All right, folks, question number 1. You see the watts, and that is power. You have mass, and you have a distance, because we're talking about energy, and you have time, because power is about time. Okay, so one thing that might help is thinking about, oh, it's a safe, okay. It's going from point A to point B. And we're looking for the vertical distance between points A and B. Let's call that H. And the other thing that you are told is that constant velocity. So whatever speed it has at A is the same as the speed it has at B. Right, so the power is the change in energy over time. And so the motor is not changing the kinetic energy, only the gravitational potential energy. You could say TME at B minus TME at A. Denominator is generally easy, that's time. But whatever kinetic energy you have at A is the same as at B, so those are going to cancel. So really the power is mgh at B minus the height at A, but let's just call that 0. Over time. And so then let's just plug in what we know. So we have 1,000, let me put this over here, we have 1,000 watts, which is a joule per second, and that's equal to m times g times the height, because that's what we're looking for, divided by the time, which is 10 seconds. So that gives you 1,000 equals 98 h. So h is not quite, they rounded g to 10, because again, in the olden days, you couldn't have a calculator on multiple choice. So it's 10.2 meters, so answer C. So again, skip to the next one if you're all set on this, but technically it was mgh at B plus the kinetic energy that it had. We don't know what the speed is, but whatever it is, it's some kinetic energy, minus, I'm sorry, h at B, so kinetic energy at B, minus no UG and the kinetic energy at A. So technically, it has two forms of energy, right? It's got potential and kinetic, and then no potential and kinetic, but these kinetic energy terms were the same because it was the same speed. So they canceled. All right, moving on to question 2. It's a little bit tricky. Person pushes a box across a horizontal surface at a constant speed of 0.5 meter per second. So the box has a mass of 40 kilograms, and the coefficient of sliding friction is 0.25. The power supplied to the box by the person. Okay, so that sounds initially like really confusing. You're like, why are you giving me friction if you care about the person? So this one is kind of tricky. So first thing you want to think about is constant speed is 0.5. So constant speed means no acceleration, which means equilibrium, so the force of the person is equal to the force of friction. That's why they're giving you friction, is because they're really equal to each other. So if you know friction, you know the person. So let's figure out what friction is. So mu is 0.25. This is a boring problem, so you no longer have to say vertical column, forces are balanced, just so you know the normal equals the weight. So 40 times 9.8, that's your normal. So friction equals 98 newtons. So that means the person is 98 newtons. Okay, so again, what is really tricky here is it looks like this isn't gaining any energy. It's not gaining height, and it has a constant speed. But what's happening is it's kind of like you have a bucket of water with a hole in it, and you are putting energy into the bucket. You're putting water into the bucket, but as quickly as you're putting water into the bucket, it is leaking out the hole in the bucket. So the height of the water isn't changing. But you're still putting water in. Okay, so that's what they're asking, is saying how quickly is the person putting water into the bucket? And then as quickly as the person is putting water into the bucket, you know, friction is equivalent to the hole in the bucket, is taking it away. So this is, I think that I'll tell you the easiest way to do it. The easiest way to do it is to use power equals FV. It's not a very intuitive formula. I will hopefully have derived it in class, but when you, it's kind of like don't know, don't care. When you can use it, it's just so much easier. So we know the force of the person is 98 newtons. We know the velocity is 0.5 meters per second. So hopefully that makes sense, that clearly the bigger the force, the more power they have, and the quicker they're moving, it means they're literally covering more distance per time. And what is work? Work is force times distance. So the quicker I'm moving, the quicker I'm going through that distance, which means I'm doing work faster. Okay, so when you multiply these two things together, you get 50 watts. Okay, so I wanted to make video answers because I think that's a little bit tricky the first time you see it. The other way to do it, and you can skip ahead if you don't want to see this, the other way to do it would be to say, I'm just going to make up some arbitrary unit of time. Let's say t is 1 second. In that arbitrary unit of time, the person pushed the box a half a meter. So I made t equals 1, right? So the power is going to be the work done by the person in the time that elapsed. So FD cosine theta over time. And we found that the force of the person is 98 newtons. The distance is a half a meter. The person is pushing in the direction of motion, so their force is to the right and the motion is to the right. The angle between those two vectors is 0 over 1 second. And you see we have the same numbers being multiplied, so we also get 50 watts. Okay, so I will give you this formula on the test. I don't love it because it feels a little plug and chug to me, but I will give you that formula. But to me, this is a more fundamental way to do it, is to really truly think about the work that the person did in a certain amount of time, but not as efficient. Okay, moving on. So this was an AP problem, and you don't know this yet, but in the olden days, each problem was worth 15 points. So 9, this is a really high average. So don't mean to make you feel bad if you find it challenging, because this is the first time we've kind of been looking at functions and derivatives. Okay, so not surprisingly, we've got the mass being pulled along a rough surface, and the position varies with time. Okay, so for those of you taking the AP, anytime they give you a function, you might evaluate the function, maybe, but you are absolutely for sure going to take either the derivative once or twice or the integral once or twice, because what they want you to know is what are the relationships between variables, not can you evaluate a function. Okay, and so that's what I would suggest. Next to each function, you can say, okay, what is x prime? It's the velocity. What is x double prime? It's the acceleration. Okay, so that's what's really cool, is that hidden in the position function, now that you all know how to take derivatives, you have the velocity function, you have the acceleration function. So question A is find the speed at time t equals 0. So a classic mistake is to plug the time in first and then take the derivative, but then you're taking the derivative of a constant and you get 0. Okay, so what you want to do is find the velocity. So in terms of notation, say, I guess I was grading the escape room. The velocity is x prime. So don't just say x prime, that's math. Say that it means something, it means the velocity. Okay, and then you're going to use your power rule, 3 times 0.5 t to the subtract 1 plus 1 times 2, subtract 1 is t to the 0, which is 1. So you get 1.5 t squared plus 2. That is your velocity. That is how your velocity is changing with time. And then we want to evaluate that function at t equals 0. So you get 1.5 times 0 plus 2. So that means that V naught is 2 meters per second. Okay, so again, that they're just testing, do you understand the relationships? And you will absolutely take the derivative of position function on the next quiz. Okay, determine the following as a function of time. The kinetic energy. So kinetic energy, plug and chug, but what we haven't done yet this year is take this function that looks like you're just multiplying things and saying, okay, but I know that the mass is 100, and that velocity is a function of time. I know what that is, so let's just plug that in. And then 100 divided by 2 is 50. Okay, I don't think it makes sense to, square that, to do a squared plus b squared plus 2ab. I think this is fine. 2 is where I think I would have gotten stuck first time through. Find the net force. What we know so far, I would have gone back and said, oh, I need to do a force diagram. I don't know anything. So that's why, again, mostly to those of you taking the AP, as soon as you see a function right next to it, say, what's my derivative? And in this case, what's the second derivative? So then your brain will already know, oh, I have A, like I have V and I have A. Okay, so, and then they love to, once you take the derivative, they love to have you combine that with something else, right? So we took the derivative once, and then we use that to find the kinetic energy. So it's just a little bit more interesting than just taking the derivative. If we take the derivative twice, we get A, which is 3t, right? 2 times 1.5. So that's my acceleration, and F equals ma. That's why they had to say net force, because we don't know how much of this acceleration is caused by the person and how much is caused by friction. All we know is in aggregate, that's how the box's velocity is changing. And then the mass is 100 kilograms and A is 3t. So the net force is 300t, which is some combination of the person and friction. Okay, and then the power being delivered to the box. So there are 2 ways to do this. The box is not gaining spring stored energy, is not gaining gravitational stored energy, so it's only gaining kinetic energy. So option number 1 is to say the power is the change in kinetic energy over time. That would be average if we took a difference. The reason this question is in tonight's homework is because we're going to take the time derivative of the kinetic energy, and that's the power. Okay, so we're going to take the derivative with respect to time. of 50 times 1.5 t squared plus 2 quantity squared. Okay, so I might muck up the names of the chain rule. I know how to do it, I just can't remember what it's called. So we're going to take 2 times the 50, or you can think of the 50s out front, that's a constant. Bring the 2 down, 1.5 t squared plus 2 to the 2 minus 1, which is 1, times the derivative of what's inside, which is 3t. Okay, and then combine stuff, and then things get a little easier because that's to the power 1. So you get 300t. So I combine the 50, the 2, and the 3. 300t times 1.5 t squared plus 2. You could distribute the 300t. I did not. I see in my key, so I guess the AP didn't really care whether you did either. So I don't know if that is rewarding or not to be like, what is that? It's just a function. But anyway, that is the power delivered to the box. Okay, option number 2 is to use that kind of plug and chug formula, that power equals F times V, because they had you find the force up above, and that was 300t. And then they had you find the velocity in whatever it was, question A. And you can check your work. These are the same final answer. Okay, so clearly the power isn't constant, right? It's t cubed plus t. All right, next question. Find the work done in the interval from 0 to 2. And for those of you who know how to integrate, if power is the yeah, you can do that. I'll do that last. Sorry. I'm just looking at my notes here. Calculate the net work done. Okay, so work equals FD cosine theta, but that is only true if the force is constant. Okay, so if the force is changing with time, you have to, or with distance, you have to integrate it. Don't worry about that. I'm not putting integrals on the test. But you should know that this formula is only true if the force is constant, and the force is not constant. It is changing with time. But you have to integrate with respect to x and not, but we know it is a function of t. I would say we want to find the work done on the box. Okay, so this is kind of tricky. But you can say, okay, wait, let's find the TME at A, because we know the speed is 2, plus our test in 2024 was just the work done by friction, but technically, I know it's been in some of the homeworks. You want to add up the work done by everything, right? The person and friction equals TME at B. And that's why they're saying, again, the net work done, I don't care how much the person did, I don't care how much friction does, because I don't have enough information. All I know is the total work that happened. Okay, so at A, it had a kinetic energy, which we can calculate, and we want the net work done. So let's leave it as that. And at B, I have a different kinetic energy, which I don't think we found yet, at 2. Okay, so at A, it was 2 meters per second squared. We found that in A. And then I don't think we found the speed at 2. So let's go up and figure out what that is. V of 0 is 2. V of 2 is 1.5 times 4, which is 6 plus 2, or 8 meters per second. Okay, so it went from 2 to 8 meters per second. Go back down here, 8 meters per second squared. Okay, so what you get is the box had 200 joules for whatever reason, it was already moving, and then the person in friction did work combined, and then it ended up with 3,200 joules. So the net work done is 3,200 minus 200, or 3,000 joules of work. Okay, so that one was kind of tricky. It just depends on your perspective, and you can see that you can figure out how much energy the box had at the beginning, at the end, and therefore the difference is what happened to it. Okay. Okay, if you don't know integration yet, you can ignore this, but another way to do this is to say the work is the integral of power with respect to time, right? Because power is the derivative, so work is the antiderivative. And we're going to integrate from 0 to 2 of our power. So what I did was I did multiply that out. So I got a nice cleaner function there that was an easier polynomial to look at. And then use the, I don't know if you want to call it the power rule, like the antiderivative power rule, right? So you add 1 and then divide by 4, add 1 and then divide by 2, and then you evaluate it between 0 and 2. So I plugged in 2. And then I plugged in 0 and got 0 for both terms. I ran out of space. And then plugged in the numbers and I got 300 joules. So that is completely legit. But again, this is just bonus for people who know how to integrate, to check your work. If you're not that comfortable with integration yet, that's completely fine. Okay, and then we're going to do a logic question. Indicate below whether the work done on the box by the student is greater than or less than 3,000 joules. Okay, so again, this was the net work done. So this is the work done by the student plus the work done by friction, and that together was 3,000 joules. We want the work done by the student, so that's going to be 3,000 joules minus the work done by friction, right, if we solve for the work done by the student. So that looks like it might be less than, but remember, hopefully you're all solid on that this year, because we just did the work done by friction. The work done by friction, sliding friction, is always negative. So this is a double negative in here. So we're going to subtract the work done by friction, but the work done by friction is negative. So the person did more energy than that. Okay, another way to think about this is that you know friction's taking energy away. So at the end of the 2 seconds, the box had 3,000 joules. You know that what that meant was maybe the person did 3,500, I'm just making that number up, 3,500 joules of work, and then friction took away 500, leaving the box with 300, right? Friction took away some of the energy and turned it into heat, so the person had to put in more to correct for the fact they knew there was going to be some loss. Okay. All right, so this is really ancient, but again, it was in my files as things where you could see how integrals or derivatives were connected. So, oh, maybe we won't do this one. I'm not sure how helpful this is going to be. Yeah, I think this is just more. Okay, I will take that off. I think that's enough practice with power. All right, that is it.